Good day, everyone. Before we talk about the work done by a variable force, let me remind you of the situation where we talked about the work done by a constant force. We said, suppose I have an object that I want to displace from location A to location B, and suppose that that displacement was along a straight line. So I'm going to displace a displacement S from location A to location B. And suppose that there's a constant force that is acting on this object throughout its motion. So at any location in the intermediate between A and B, I can think about the force acting on it with some angle theta. And we said that if that force is constant throughout the displacement, then the work done by this particular force as the object is being displaced, the displacement S from location A to location B can be given by the dot product of the force and the displacement, which of course you can always write the dot product as the product of the magnitudes multiplied by cosine the angle. Otherwise, you can think of it as the component of the force in the direction of the displacement multiplied by the magnitude of the displacement. Now, suppose that that force is actually not constant. Suppose the force depends on the location. How would you deal with a situation like this? It is possible that the direction of the force would be changing or the magnitude would be changing. So one of these two things could be changing or both. But for simplicity, let's just deal with the situation where only the magnitude of the force is changing. The rest follows the same way. So without loss of generality, we're just going to deal with the situation where I am displacing along a displacement that is along a straight line from point A to point B, and the force is acting on that object, and let's say it's acting in the same direction as the displacement for now. And then the magnitude of the force depends on the location. So if I call this my x-axis, then at this location, this is my xa, and at this location, the value of x is xb, and the force varies depending on x, and I want to find the work done by the force. Now, how does the force vary? Again, let me just think in general. I can write an expression of how F depends on X, but suppose in general I'm thinking about a force that changes with the position, something like this, for example. Just to give you an idea of how we're going to proceed with this kind of analysis. Now, what I could argue is that at some point here, at this particular X, I can argue that the force here, if I just take a very small delta X, at this location X, if I take a small enough infinitesimal displacement, then I can argue that the force is really roughly constant in this location. That this force at this particular location X is roughly constant, in which case I can use this story here. I can talk about the work done by a constant force. So I say the amount of work that is done during this very small displacement delta X is given by the magnitude of the force, which I'm going to say is constant, multiplied by the displacement, which is very small, the infinitesimal displacement dx. And that would be the very small amount of work that is done during this very small displacement. And then if I want to think about the work done during the whole situation, going from A to B as the object displaces from A to B, then I can talk about that as the integration of the work all the way from situation A to situation B, which I can write as the integral of f of x dx. And now since I'm integrating over the x variable, then I can call this an integral from xa to xb. And this is how we're going to proceed to find the work done during the whole displacement from xa to xb. Let me give you an example. Suppose we're thinking about this situation here, where I'm launching a projectile from Earth, And I know that the force of gravity, if you remember, the force of gravity between two objects was given by Newton's universal law of gravitation. He said, suppose I have two objects of masses m1 and m2, then they're always going to attract each other with a force that is given by magnitude wise, is given by some constant times the magnitude of the first mass times the magnitude of the second mass divided the distance between their centers squared. And this force is always going to be attractive, meaning it's going to be along the line connecting the two centers towards each other. And of course, we know that this force would be equal in magnitude and opposite in direction. So if I think about an object being launched from Earth, and I want to think about what is the force affecting this object in its journey. So if I draw the free body diagram of this rocket, it would just look like it only has one force acting on it, and that would be the force of gravity. And in this case, it will be equal to g times the mass of the rocket, m, times the mass of the second object, which is Earth, divided by the distance between them. Now, the distance between them varies because that object is moving away from Earth. So the distance between them, let's call it r, and it's going to be magnitude-wise equal to r squared. And this force is going to be in the direction opposite to that vector because that force is always attractive. So Earth is applying that force towards it. So magnitude-wise, it's given by Newton's universal law of gravitation. But if I want to think of it as a vector, then it will look like it's in the negative direction of the unit vector r hat. R hat is a unit vector in the direction of this vector r. So this is how big the force is. And obviously, as the object gets further and further away from Earth, then this r changes, increases. So the force decreases. Now, suppose I want to think about the amount of work done by this force as the object goes from situation A to situation B, or when the rocket was here versus when the rocket is at location B. We can apply the same rule that we just worked out here to think about how to calculate the work done. I can think about the work done during a little bit of an infinitesimal displacement dr, and then take the work done during that little bit of dr and then expand it, integrate it over the situation from location A to location B. So let's plug this in and see how that would work. Not to be a pun. So little dw, that's the work done as I go from r to r plus a little bit of r, an infinitesimal displacement dr. So that's given by the force at location r, which I know, which is given by magnitude y is given by the universal law of gravitation, and it's in the direction r hat. And then I dot that with the little dr because that's the infinitesimal amount of displacement. Now r hat and dr are in the same direction. So the dot product of these two would be just equal to the magnitude of dr, right? If I just think about the dot product here, that would be the magnitude of r hat, which because it's unit vector, that means its magnitude is always 1, times the magnitude of dr, which we're going to call dr without the arrow, times cosine the angle between them. But the angle here is 0 because r hat and dr are in the same direction. So this works out to be negative g times the mass of the rocket, the mass of Earth, divided by the distance between them square at that particular location, times the magnitude of the infinitesimal displacement dr. Of course, this is a scalar product, so it outputs a scalar, which is a good thing because the work is a scalar quantity, so I'm expecting the whole um, expression here to give me a scalar. The other thing here that I like is that this came out to be a negative quantity, because here I'm expecting the work to be a negative quantity because the force of gravity is in the opposite direction of the displacement of the rocket as it moves away from Earth in that little infinitesimal dr. So I'm expecting the force of gravity to do negative work during that little displacement. So in essence, it's contributing to slow the rocket down, as opposed to maybe there are other forces that are acting on the rocket that I did not include here on the free body diagram, which is maybe, the thrust and so on. That might be speeding the rocket up, is be doing positive work. Now, in essence here, if I look at what we've done, suppose I plot this force, a force that goes as 1 over x squared or 1 over r squared. In essence, what we've done here is we said, suppose I calculate the amount of work done during a very small amount of displacement from, let's say, from here to here, right? And now what I want to do is I want to say, suppose the displacement is much bigger than that infinitesimal displacement. How can I think about the work done during a displacement from some situation A to some situation B? So that means I need to integrate this expression. So I calculate, I say, therefore, if I want to calculate the work done to go from some location A to some location B along this path, then that would be equal to the integral of that infinitesimal work from situation A to situation B, which would then look like that little amount of work has negative g times the mass of the object times the mass of Earth. All of these are constant things, so they can come out of the integral. And now I'm integrating dr over r squared, and because I'm integrating over r, then I'm going to substitute with the limits from ra to rb. The integral of 1 over r squared is equal to, of course, increase the power by 1, so it becomes x to the negative 1, and then divide by negative 1. So it becomes negative 1 over x. So the negative cancels with the negative here, and I'm left with g times the mass of the rocket times the mass of Earth multiplied by 1 over r, and the limits go from ra to rb. So then this becomes, you might be scared a little bit because you say, oh, hang on a second, the work is no longer negative. But just stick with me for a second here. Because when I plug in the upper limit minus the lower limit, 1 over rb minus 1 over ra, rb is actually larger than ra. So 1 over would be smaller than 1 over. So I recover my negative sign. This work is definitely going to be negative if ra, which would be 0 for ra smaller than rb, because then 1 over ra would be larger than 1 over rb, and I recover my negative sign in the work done. So suppose I want to know exactly if situation A is the rocket right on the surface of Earth. So its distance from Earth is the radius of Earth, and I want to launch it all the way to some location here that is a distance r. Then in this case, I can plug into this situation here and say, calculate the work done to go from the radius of Earth to some r. Then I can just use this expression, g times m, the mass of the rocket, times the mass of Earth, of 1 over r minus 1 over the radius of Earth. So I'm able to calculate that work. And again, r would be larger than re, So 1 over r would be smaller than 1 over re, and therefore this would give me negative amount of work, which I'm happy with because the force of gravity is against the displacement, so I'm expecting the work done here to be negative, the work done by the force of gravity. Now suppose that I want to know next, take the limit r goes to infinity to determine an expression for the work needed to launch the projectile to an infinite distance from Earth. So suppose that I want to take this rocket all the way to infinity. Of course, as we've talked before, infinity doesn't exist in physics, but we're just thinking a very large r. So suppose this r goes very large, then what would be the work done in that case? So suppose I want to launch the rocket from the radius of Earth to r that is approaching infinity. And when r approaches infinity, 1 over r approaches 0. So this becomes g times the mass of the rocket, the mass of Earth, divided by the radius of Earth. Because this term became 0, the one with the 1 over r became 0. So I'm left with the negative 1 over re. The next piece says, use the work energy theorem to determine an expression for the initial velocity v naught so that the final velocity is 0. This is called Earth's escape velocity. So suppose at the very beginning, you give the rocket some initial acceleration to launch it with some velocity v naught, and then there is no longer any acceleration. So I just know its initial velocity. It's almost like throwing a baseball. You give it a little bit and then you let it go. And after you let it go, it's under the influence of gravity alone. So you say, suppose I give it some energy to start with by giving it some initial velocity v naught, and then I want that velocity to take it all the way to infinity. What would this velocity be? So if you recall here, I would say, think of it this way. You want to ask yourself, how much money should I put into my checking account such that when I spend all of that spending that is taking the money out of the checking account, putting it into, then how much money should I have at the beginning? Well, you should have exactly the amount of money that is needed to spend all of that work against the force of gravity, right? So the idea then to say is, suppose that here's the situation. At the beginning, situation 1, I want to give it some initial velocity v naught, and then I want it to get to a position where r is infinity, but I don't care that it has any velocity once it gets to r infinity because I want the minimum velocity to start with. So I want to say I want it to be at rest when it reaches infinity. That's the setup. So situation 1 here is at the surface of Earth, and situation 2 is when it's at infinity, but I don't care that it's moving at infinity because I don't want it to go beyond infinity. I just want it to reach infinity. That's sufficient to me. And if you recall, the work energy theorem says that the network, all of the work that is done on an object, is going to change its kinetic energy. So the work done then to take the object from situation 1 to situation 2 would be equal to the kinetic energy at situation 2, because the change in anything is final minus initial, minus kinetic energy 1. Now the kinetic energy at situation 2, we've decided that we want that to be 0. I don't care that it's moving. The kinetic energy at situation 1, that's how much energy I gave it at the beginning, V naught. So it's half times the mass of the rocket times V naught squared. And of course, the work total that was done on it is this amount of work because I want to take it all the way to infinity. So that's minus GMME. This is the amount of work to go from situation 1 to situation 2. So that's the amount of spending that you've done. So that's equal to the difference in the balance between the beginning and the end. So I can use this to find V naught. So multiply both sides by 2, divide both sides by m, and then take the square root. And of course, mathematically, when you're taking the square root, you take positive or negative, but here positive or negative are meaningless because you're just thinking about the speed. And the speed, of course, is always positive. So this is how fast I need to launch the rocket to get it to overcome all the work done by the force of gravity. This is called Earth's escape velocity. If you launch anything with this velocity, you notice that it doesn't depend on the mass of the object itself. So any object that you launch with this velocity, if you can throw a stone this fast, you can actually get it to escape from Earth. Now let's plug in some numbers and see exactly how big that velocity is. Well, if you recall, G was 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. The mass of Earth, of course, is 5.98 times 10 to the 24 kilograms. And the radius of Earth is about 6,000 kilometers, 6,300 kilometers. So 6.3 kilometers. So 6,300. So I'm left with 10 to the 3, but I also need another 10 to the 3 to get it to meters. And then that would be the radius of Earth. So if I plug these numbers in, I find that I need to escape Earth. Any object that goes at 11,000 meters per second will escape. So if you throw any object at 11,000 meters per second away from Earth, it will escape Earth's gravity. The next piece here is a similar piece, but instead of thinking about Earth and escaping from Earth, you're thinking about the escape velocity from a black hole. So the whole difference is that instead of thinking about the mass of Earth, you're going to think about the mass of the black hole, which is 3 times the solar mass in this case. And then instead of the velocity is something that you're looking for, you actually have the escape velocity from the black hole, which is the speed of light, which is 3 times 10 to the 8 meters per second. And you could play the same game with the work energy theorem. And you say, I have G, I have the mass of the black hole. I'm trying to find the radius of the event horizon. And in this case, I do have the escape velocity, so I can find the radius. So see if you can work this out. Now, there's one little extra piece here that I wanted to point out to you that is not related to this problem, but a general kind of statement to think about. Recall when I told you that for any conservative force, the work done by that conservative force is given by the negative of the change of the potential energy associated with that particular force. So here, if I think about the work done by the force of gravity, if you scroll up, you'll see that it's GMME times the radius, 1 over the radius at B minus 1 over the radius at A. And that's equal to negative the change. Now, the change in anything is the potential energy at the end, where here's Earth and here's the rocket at some location A. That's initial. And then the final is when the rocket is at some location B. So the change in the potential energy from this situation to that situation would be the potential energy for the configuration B, where the rocket is separated by a distance RB, minus the potential energy at situation A, where the rocket is separated by distance RA. Now, if you examine these two equations, you'll find that here there's a term that only depends on B. So I can associate that with the potential energy at B because it has nothing to do with the situation at A. And another statement here, another term here that only depends on the situation at A. So in other words, I can write it like this. In other words, I can associate it, that first term, which is only at situation B, with the potential energy of configuration B. And I can associate this term, which has something to do with only situation A, with the configuration at A, the potential energy at the configuration at A. In other words, I can write a general statement about what the potential energy at some location, at some configuration of Earth and some objects separated by distance are. I can say that the potential energy contained in this system here, in this configuration, is equal to g times the mass of the object times the mass of the second object, which is Earth in this case, divided by the distance between them. That's a general statement about the potential energy stored in a configuration of two objects that are separated by a distance r. This here is the most general statement about the gravitational potential energy. Sorry, with a negative sign here. The negative sign is critical. So if you wanted to plot this, what would it look like? Well, it would look something like this. Because it's negative, so it's all below. So if this is the potential energy as a function of r, and I want to plot it, 1 over r, when r is 0, then this is infinity, but with a negative sign, so negative infinity. When r is really, really large, so infinity, then the potential energy would be roughly 0. So this is a curve that looks something like this. I don't know if I'm getting my scale right, but it looks something like that. That's the potential energy. So the work that you've been doing, anytime you want to escape, it's like you're trying to escape out of that well. If you want the rocket to escape Earth, it has to escape out of that well to get to infinity where it's free. As long as it's within some distance, it's always going to be below the zero potential energy. So that means that it's a negative potential energy. So it's more preferred by the system. The force of gravity is always trying to get you down that hole. For you to escape, the story about the escape is a story about trying to get yourself with a potential energy of 0, so that it really doesn't matter that Earth is there. That's one way to think about it, that you're trying to put yourself at a location where it really doesn't matter that Earth is there. You've escaped the gravity of Earth. But wait, there's more. For those that are interested, there's always more. Here's a little piece that you might find super interesting. I personally do. Sometimes we write the relationship between the force and the potential energy like this, that for any conservative force that is associated with a potential energy, I can always write the force as something that we call the gradient of the potential energy. This is typically how we write it. But of course, I told you, is another notation for potential energy. Now, what is a gradient? A gradient is a mathematical object that represents the slope, but it turns a scalar quantity into a vector quantity, right? So if you think about the surface of a sphere, for example, and I ask you, at this particular point, what's the gradient? You're thinking about the direction in 3 dimensions of the slope at that point. That's really what the gradient is. Now, because the potential energy here only depends on 1 dimension, or it has a certain symmetry, so I can just think of it as just being dependent on 1 dimension. The gradient in that case has a very simple form. It's just in the direction of r, the derivative with respect to r. It's just a generalized slope. It's a fancy way of thinking about a slope, but it's a slope of a surface as opposed to a slope of a line. Here, because it's one-dimensional, then I'm thinking about a slope of a curve. So what I'm saying is that the force is the slope of the potential at whatever point r. So here it's a high slope, so I'm expecting a large force. Medium slope, so medium force. Small slope, that means small force. So I'm expecting that the force actually gets smaller as we get far away, as r gets larger and larger, which is something that we know, that the force of gravity gets smaller as r gets bigger. The other point about the negative sign here is to say that the force is actually in the direction like this. That's what the negative is indicating in this case, because r hat would be in the increasing r, so the force is attractive force. So when you're inside the potential well like that, the force, think of it as the potential well is pushing you towards the zero, is always pushing you towards the zero like that. And then, of course, the expression for the potential energy we just found, that's negative G times M times ME over R. Now, what's the derivative of that? Well, the derivative of 1 over R is 1 over R squared, right? So you can think of it like that, negative R hat, negative G, M, ME, constants, like let's take them out of the derivative. And then I'm taking the derivative of R to the negative 1. So that brings down the negative 1, and then I decrease by 1, so I get negative 2. So this is the negative of 1 over r squared. So I'm still hanging out with the r hat here with the negative, and then I'm still having the negative g me here, but then the derivative will give me negative r to the negative 2. So 3 negatives here, I'm left with 1 negative, and that's g me over r squared in the direction r hat, which is exactly what we started with the force of gravity. And that's always true. See if you can apply it to the elastic potential energy. Have fun. Enjoy.